Hi. Good. So let's get started. I can see it's getting cold. I hope you feel well. I don't know if it's cold or not, but it's not very cold. It's somewhat cold, but I can see many of you have jacket. As many of you are sitting, then must be cooler than usual. So just to make sure that you are not too cold. If you need to stand up and walk a little bit, feel free to do it, because do some stretching to make your body feel warm. It's okay. Don't bother. I don't mind that. I mean, if you need to walk a little bit to make yourself warm, please feel free to do it. Okay. So now we are trying to close this long chapter, hypothesis testing. I'm not sure whether I can finish. I suppose can finish, but as experience from the other section, they want me to go slower. Okay, so I intend to finish, but if not, then I just leave the rest for the next class. It's okay, because we can go fast on other subjects, so make sure everything is done. Or if I'm unable to finish everything, then I will just reduce the scope of exam, so that you don't have to worry about that. So if we don't have time, then we just have other way to do it, right? Because of all my previous lecture have been recorded, so if I fail to complete some part, you can watch those. Okay, so but if I don't finish, then it will not be exam, so don't worry about that. So because it's important to have concrete understanding of what we cover, rather than I cover so fast that you don't get anything, right? So it will be more important. So let's quickly resume what we have done on Wednesdays. That's a little bit after 1 or 2 days, probably you may not have perfect memory. So let's quickly review what we have done. Okay. So to recall, the idea hypothesis testing is the following, right? Remember estimation. So let me draw a picture. I think it's good to have a picture here. So estimation, remember our starting idea, right? Is like you are hired by, say, a businessman, right, Elon Musk, right, to investigate, right, how much people want to pay for a new car or a new phone, right? If you're targeting a Chinese market, which has 1.4 billion people, right, you can't ask every single people how much you want to pay for your product, right? So the ideal estimation, again, is like you have something we want to study is called population, right? And you are interested in many things, but in particular, you focus on the mean meal, right? There are many people here, right? And you want to say, in this case, is how much they want to pay for the new product, right? And the idea is you don't know this meal, you want to know it, so that you want to see if you want to enter the market, right? You work for Elon Musk or some other businessman, right, or company. So what you're going to do is, okay, we randomly pick some people here, okay, and look at the sample mean and hope that this will be a good estimate, right? That's called estimation. Okay, it's from what we call sample, right? Our knowledge from sample, and to estimate, we don't have any idea on the meal. Okay, and now the story goes on and say, okay, now after a year, right, and we enter the market, right? The Elon Musk or his company in the market, and the question would be, okay, so we want to evaluate how the performance of the product, right? Is it up to the standard, right? Is it up to guess what we estimate the meal, our knowledge of meal, is it going to be correct or not, right? Or after a year, is our meal is going to be different. Our understanding of meal is different, right? Suppose after a year, now the economy is open, now things changes. Now our presidency met President Biden, right? Things changes. Maybe the new things goes on, and is it meal going to change or not, right? So it just reverse, right? We want to we have some knowledge about this. We want to check by the data. That's hypothesis testing, right? So that's the idea. Okay. And so far, the way we learn is depending on we know the sigma or not, right? We know sigma is called the Z test, right? If you don't know sigma, it's called the T test, right? And it really depends on whether you know the sigma square, okay? So I guess the big picture, right? So let me review the procedure. I will go over the 3 examples again so that you would have a more concrete understanding on the 3 main way we do it, okay? So we call this example, okay? This is the right tail test, okay? And we assume that the population follow a normal, it's a bell curve, right? The bell curve. And with standard deviation 4, right? So just to remind yourself what does that mean here, right? It means that our leading example, right, was a case where, okay, this is the distribution, right? And it's normal, right? With standard deviation 4, okay? And under the null hypothesis, it is 6, right? This is assumed to be the distribution over the population, right? And there's no uncertainty here, right? For the underlying population, right? It just, if you draw something, then it becomes a probability, right? But how it distributes, right? It's a bar graph, right? Suppose we assume that, right? And what actually we do, right? We draw a sample, right? We draw a sample here, right? And the sample here is still 6 here, right? But the shape of this depends on this, right? Maybe I use a better notation here, square 16, right? Then this one, right, will be sigma over n, right? The shape of this sample mean, right, will depends on how many n you have, right? The bigger the n, the more squeezed they are, right? And how spread depend on originally how spread is, right? So now the question is, we look at the data, is it going to favor our H0, H1, right? We have to decide, right? Whether we want to say the data supporting this one or this one, right? We want to see if actually, right, as we said, right, the example is, are they willing to pay $6,000 for the phone, right, or more than 6,000, right? After now, things changes, right? And if you can see this, and then very naturally you would think, right, it's more than 6 or not more than 6, right? So it means that if it is too big from 6, right, from that onward, right, we will say reject, right? Reject action now, right? Then this like don't reject, right? So that is what we call, this is the critical value, right? This critical value. Okay. And how we decide this critical value, right, is how we decide that is far away, far above 6, right? Is saying this area is very small, right? And this area turned out to be alpha, right? Which is the probability. Even this is true, we make a mistake, right? We have to decide the alpha. The level of type 1 error we are going to accept is determine the location of the critical value, right? The smaller the alpha, the bigger the critical value is. And to remind yourself, there's no free lunch. If you set a smaller alpha, you have a means you small type 1 error, you have bigger type 2 error. Type 2 error means that this is wrong, but you fail to reject. Okay? So as a balance, alpha is used to be 5%, right? Just like those who study in the law, right? They say no free lunch, right? If you make a criteria more strict, then you have some issue, right? Just like you punish a minor crime heavily, right? Suppose you just send everyone to jail forever for minor criminal activity. That means that your power to deter people to commit a major crime would be less, right? People would not think killing people, right, would be different from committing a minor crime, right? So that's why you have to be very careful, like here, right? You have to be very careful how to set alpha, but usually we do is 5%. So the question is large enough, right? 5%, then we're done, right? And since we know sigma square and n, then this number is the critical value will be well known, right? There's no problem to figure that out, right? And we can easily change it to the thing we know very well is called the z, right? The z, this become 0 here, right? The critical value. If this is alpha, it is denoted by z alpha, right? That's the notation we have is the tail area. The area on the left is alpha. That's the number, right? So it's slightly different from f. F is the area on the left, but the table you look at is the left tail area. This is z alpha is the right tail. Okay, and this is called the critical value method, right? Whenever your data is here, you reject, otherwise you don't. All right, and you can remind you if 5%, right? And in Excel, you will be looking at the left tail area, right? Norm dot this inward, right? It's 0.95. Okay. The reason is alpha is 5%, and you look at the left hand side. Okay, and this turned out to be 1.64. Okay, and you look at your data, okay, which is, let me use the color pane, it's like 7. Okay. 7 is here. Okay, why 7 is a rejection region? Because 7 is actually here, which is 2. Okay, why is 2? Remember what is Z means? Z means here is how many SD from the mean, right? 7 to 6 is 1, and SD is 1/2, right? 1 over 1/2 is 2. So that's why there's 2 SD, and it's far enough from 0. We will call sufficiently small, right? It's very unlikely that actually happen if H0 is true. So we will consider this is no longer something we can take. We take this guy, right? So we'll reject H0 at 5% certificate. Or you can do the p-value thing. Look at the area on the right-hand side of 2, right? Which is p-value, right? The p-value will be, if you care, will be the norm as this 2 true, but this is not the end because this only gives us the left hand side, 1 minus right hand side. Okay, so this is the p-value. You compare 5%, then that's what you do. Okay, so since you really can't make the set value, you can do it in the using this table, so this will be fine. Okay, both method you can use it in exam or assignment, because even though I use the formula, but you can actually check the table. Okay, is there any question? If no, then I look at, now let's look at the other example. Look at the case where we don't know this, right? Because in general, we don't know this guy. Okay, then how can we proceed? Okay, and of course, one thing you ask is, in general, we don't know sigma. Why I still talk about this? The answer is, if your sample size is large enough, there's no difference between T and not T. Okay, because T is same as that. So the procedure will be same. Okay, so that's why we keep this as the way when you collect data, you have very big N. There's not much different. Of course, you have to make assumption, right? The underlying is spelled, but like, because the key part is you have to make assumption like this one, right? The distribution, the underlying, what it looks like, how much we need to pay in China, 1.4 billion people is following this, right? That's why the sample mean is also a bell curve and everything goes, okay? And you probably ask, what if this doesn't hold? it's way beyond our class. When you study master program, then if you want to, then you will study that. But you would always maintain the assumption that always the bell curve. Okay. Now, and let us go to the other case where we call the T distribution, if there's no question from you. Okay. So slightly little bit repetitive what we're doing, but I hope this become I will do the T one, not this one. I will do the T. So let me do the T left hand side. So I'll do this one. Okay. So this question again, okay. We have the population follow normal. Okay. Again, what we have is 1.4 billion people. Okay. How much they want to pay? Follow a normal distribution. Okay. Do note that again, when we say the population follow normal population, there's no randomness, right? A normal distribution, what we mean is suppose we do a random draw, it's normal. But remember, underlying the population has no randomness. Okay, it's there. You just don't know. But if suppose a random draw, it's a normal. But there's a bell curve here. Okay. And now we have a sample, right? With size n equals 16 and sample is 3. So what we're doing is we have drawn a sample there. Again, it's a bell curve. Okay. And under the null, this is 4. Okay. So this is originally 4. And because sample means unbiased, this is also 4, right? Both are bell curve, right? Because the original is bell, then the sample mean is also bell. Okay. And originally, this is sigma square. Okay. We just don't know it. Okay. And this is also sigma square over n. We know n, but we don't know sigma. So we still don't know that. Okay. So there's a trouble here, right? Because we want to look at our evidence, right? Our evidence, what we have is 3 here. Okay. 3 is here. So the question is, we want to compare ourselves whether we are favoring x0 or x1, right? Whether mu is 4 or mu less than 4. So are we going to say our data is 3? Is it going to favor 4 or less than 4, right? Because even 4, by chance, because the bell shape, it can go to less than 4. That's also feasible, right? So is it sufficiently lower than 3, right? So as we're saying, the distance is far away enough, right? Far away enough is our question. And again, because probability, far away enough, we quantify as, is this area small enough? Okay. And is it small enough? We have to give a criteria. What is small enough? That's called alpha, which, as I again say, this is 5%. And again, because probability is a normal, everything is possible, right? Normal come from negative infinity positive, right? So we have to decide small enough is 5%, right? This is a type 1 error. Even this is true, it has happened. So it's 5%. So now how can we proceed? The problem is we don't know this sigma. We have no n. We have n with no sigma square, right? So how do we calculate alpha? Right? There's no way to do it. Okay. And the lucky thing is we have samples that in this one. Okay. And turn out that if we do the same procedure to calculate x bar minus mu over s over root n, okay, this is SD, right? We do that instead of this, right? Because before we have that, right? And if you do that, right? Before is the standard normal z, now become a t, right? Tn minus 1, right? So that means that original is a bell curve, okay? That one still have a bell, but a little bit slightly different from the bell, right? The bell is slightly fatter tail, okay? And T bell has different version, not just one version, right? The version you have to look at depend on the sample size. It's the m minus 1th one, okay? So that means that what we have is here we have orange color, right? This is Tn minus 1, right? Looks like this. This is 0 here, okay? And this 3 become -2, okay? just again do the same procedure, right? 3 is 1 below 4. Look at the SD, right? Standard sample standard deviation over the root of n, right? Which is 1/2. So is 2 SD below the mean, right? And this one we know how to look at, right? This is a table. We can calculate this area. So again, we ask this area is less than 0.5, 0.05 or not, right? So from number to area, that's very simple, right? It's just T, this, right? -2. Now n is what? N is 16, so it's 15 here. The 15 table we're looking at. And because the area on the left-hand side, so this is exactly what we want. We don't need to subtract from 1. Okay. Is that okay? So the other way around, you can do critical value, right? Critical value is looking at what's the threshold you reject, right? So just to remind you, we do is like we are trying to, so this is asking 5%, right? So we want to look at this, right? And if this is alpha, right? 5%, what's the number of that? And we can look at this, right? What's the number here? Such that this is 5%. Okay. And how to do that, right? From area to number, right? Just the inverse. We want 5% in looking at the 15 one. Okay. And turn out this is to be -1.753. Okay. And that means that as the number is as withdrawn, -2 is here. So it's inside, then you reject. So you need to do only one way for your assignment, right? Either critical value or p-value. And of course, some of you are wondering, how can you do this in exam? The answer is no, you can't. You have to do critical value. Okay. You really can't do it. But again, you can still do something. You can do p-value, but you will do that one. Okay. Of course, in the very rare case that shouldn't happen, but in the case that I got crazy, I didn't aware, then you just give me this answer, will be fine, right? In case I ask you the p-value, I mean, you can give me this one, that should be fine, okay? But well, unlikely I would do that because anyway, our TA is try to check my exam, so it should be okay. Okay, is that okay? Okay, is there any question? I know it's a bit review, but because today we talk about the same thing again. So that's why I make sure that everyone is fine. Okay, no problem. Then let us review the last thing, this two-sided two-tail test. We need a little bit review because so just to remind you, special case for binary data is the mean and the variance are related. That is because the binomial, right? Mean, the variance is given mean minus 1 minus mean. So that's very special case. Okay. So let's go to this. Okay, binary case. So remember the leading example we have for this is to check the gender ratio in the B school, right? In CHK, and it's well known that 40% of the student, undergraduate student, are female. Sorry, 60% are female. So 40% are male. So this is what's trying to see. I want to collect the data of 50% student, and I figure out that half of them are male and half of them are female, or like this class today, right? And I want to see whether our understanding 0.4 is correct or not. So this is an example. So if we try to do it, right? So the sample proportion looks like this, right? Will be 0.4 here, right? Because this is an unbiased estimate, okay? And one interesting part is the variance we know. The variance is 0.4 minus 0.4 over n, right? So once we fix the location of the mean of the proportion, we fix the shape. Okay, of course, the bigger the n, the more narrower, but we know exactly what it looks like. Okay. So again, the question would be, we want to check if actually it's 0.4 or not 0.4. Fair enough, right? So because we are going to take the evidence on both sides, that means that it is sufficiently small or sufficiently large, then we're going to take H1, right? So that means that if small enough or big enough, right? There are two critical values here, right? And since we don't know where it is, it's symmetric, right? Then we will put alpha over 2 here, alpha over there, right? Remember, alpha is type 1 error. Even this is true, what's the probability we commit this mistake, right? So if too big or too small, then we will in favor of H1 rather H0. Okay, so that's the idea. Okay, and since once we fix the n, right, we know how to figure that out, right? So if it is in this region below that or above that, then reject, right? That means that if you look at this, the z, right, you can convert to z. This is 0. Okay, and this is alpha over 2, and this alpha over 2, right? So this is what? This is z alpha over 2. This is, because symmetric, this is negative z alpha over 2, right? Remember, this means the tail area, right? The right-hand tail is what? So now, just to remind you how to find this is just normal, standard, area, go back to the data, inverse, okay? You use 5%, so the tail will be 0.025, okay? And this is 0.975, okay? Because this is 0.025, look at the left-hand side, 0.075, okay? That will be done. If you like this guy, this is norm dot s dot inward 0.05, okay? They give you, this gives you negative 1.64. This gives you 1.96, right? So either way, you would know you reject if your data turn out to be more than 1.96 or less than negative 1.96, okay? And what you do is you calculate that is turn out to be 0.5 here, okay? 0.5 here. Asking, is it sufficiently big enough, right? Turn out this 0.5, when you convert, right? How you convert? Look at the distance, which is 0.1, right? And over the square of this guy, because of variance, how many SD? Turn out to be 1.44, right? And this is not in the region, so we don't reject. We will say it's still 0.4, right? We do not reject, or we fail to reject, okay? And those of you who want to calculate p-value, it will be this guy times 2. Why? Because you compare with alpha, right? Not alpha over 2, right? Or the definition of p-value is you adjust the alpha such that it just rejects, right? So it would be, the p-value would be norm as this 1.44 true, okay? But this is the area on the left-hand side. So you one subtract from that, give you the right-hand side area. You multiply by 2, and give you the p-value. Why multiply 2? The two-sided one, multiply 2, because you are looking at adjusting the region of blue such that this just reject, right? So you have to calculate both sides, right? Or you can imagine the reason is you compare this area to alpha over 2, right? Because before you do that, you don't know whether left and right, right? So that's the reason. Okay, you multiply 2. Okay, this is a convention. Okay, so don't ask me why we don't compare to alpha over 2, but that's the way we do. Is that clear? Any question? Because we'll be doing the same procedure for the rest of the day. Okay, so hopefully you fully understand what are we doing. Okay. Now, if there's no question, okay, and then we proceed. Okay. Now we do 2 samples. I think at least we have time to cover the first 3. Okay, and depends on how fast I can go. We may leave this for the next, but I hope we can finish. But always we are fall behind the plan a little bit, but it's okay. So what actually we are working on is looking at 2 different populations, and why we care this. Okay. Remember the question we said at the beginning. You are selling the product, a new product to China, 1.4 billion people. And you may imagine they're supposed to selling a car or a new phone, right? And probably the taste for the man and woman are different, right? Maybe you are trying to sell a pink color phone or pink color car. Probably it attracts more women than men, right? So on and so forth, right? Depending design, men and women are different, right? Or people in the north or people in the south are different. People in the coastal city are different from people from the inland area, right? So the question would be, how would you do that, right? So you consider 2 types of population independent, okay? And they have different mean and different variance. By independent means if I know something about the man has no meaning on the woman, right? If I say, I know men want to spend $5,000 on the new phone, doesn't tell me anything about woman. Of course, it's an extreme assumption, but that is useful, right? You can care about covariance, so on and so forth, but let's start from something easy. Assume anything you know, you draw someone from population 1 has no impact on population 2. Okay. So here we have some notation which is a little bit heavy. If the first time to see it, your mind will be a little bit uneasy. That's what I learned from the previous class. So let's draw a picture, hopefully that to make sure that you would be easy to see. Okay. So as I said, I have China here. Okay. And I divide China into 2 groups of people. One are the men, I call population 1, are the men. Okay. And another population called population 2 are the female. Okay, are the female here. Okay. And you can imagine that the male will have their own mean, we call mu1, right? And I have their standard, sorry, I have the variance called sigma 1 square. Okay. And later you will see I will assume the bell so that you can imagine this like this. Okay. Mu1 here and sigma 1 square. Okay. And similarly, I have female here, right? How much they want to pay? Average is mu2, right? Variance sigma 2 square, right? Later, I'll assume they're normal anyway. So you will have this type of graph. Okay. So this is the graph we have in our mind. Okay. And we have guy number 1, number 2, number 3. Okay. What he going to pay will be x11. What he going to pay will be x12. What he going to pay will denote by x13. Okay. Similarly, we have woman number 1. Okay. So it will be x21. Okay, and number 2 woman will be x2, 3, and number 3 woman will be this is x2, 2 and x2, 3. Okay, so of course there are many men and women here. Okay, many woman, men here. Okay, and now suppose we collect data, right? And we only get the first 3 guy. Okay, suppose I get the first 3 guy here. We got a sample. Okay, and we call sample mean, right? We're very simple. We suppose we have only 3 person, right? We'll be just add up the 3 guy, right? Will be just x11, x12, and x13 divided by 3, right? And number of the sample 3 is actually we call n1, right? You can samely define what is S1 square, right? Calculating the sample mean within them, right? And similarly, we can define what is x bar 2 as a sample variance. Suppose we get 3 of them or 2 of them, doesn't really matter, right? And we also have S1, sample. Okay, so all of them can be well defined. Okay, we just extend from 1 to these 2, right? They're no different. And because they're independent, there's no interaction, right? That independent thing. Is that clear? Now, here comes a slightly more difficult part here. Okay, this is definition. X11 is the first guy, X1n, right? We can calculate the sample mean, and because of the random sample, right? Sample mean is unbiased, and variance is just basically the standard error, right? It's based on that. We know it. There's nothing new there. Okay, nothing new, just same thing here. Just but one more subscript. Okay, slightly little bit notation, but not really there. And do note that the sample variance is -1, so there's nothing new there. Okay. Now here comes a slightly little bit tricky, right? And the bell curve. Okay, and this is the sample mean is also bell, so that's important. Okay. Now here comes the most difficult part that we are going to use today. Is we use the knowledge saying that 2 bell curve, the difference is still a bell. Okay. Why is true? Let me recall what we have learned, but probably you are not aware that we talk about this. We talk about random variable here. There's a graph that I mentioned that we'll use later, which is exactly what we are going to use, is this graph. Okay, remember this one, especially below 1. Okay, we're saying that the integral x a bell, red is a bell. Okay, you take the difference, still a bell, variance add up. Okay, so why we care about this? Okay, the reason is we want to look at, okay, whether look at the difference between the sample mean. Okay, difference of sample mean will have a normal as a bell curve, depends on whether originally they're different and variance set up. Okay, why I care about that? So let's go back to here. So what we want to say is, okay, let me rewrite that in the other slide so that makes sure that it's clean. Okay, so what we have is I have a man's going to pay. Okay, it's here. X, right? We have mu 1, right? X1 by sigma 1 square, right? And because of the normal, right? this is also a bell, right? Same mean, but the variance strength, right? I think we learned that many times, right? The same, we can go for the woman, right? Oh, sorry, I should use red color, not red enough. So X2 is a woman, right? Woman want to pay is also a bell, and I have the bar graph, but the sample still center here, but of course different shape. The shape depend on how much sample you got, right? And yeah, I should be a little bit more careful. Maybe I need a little bit narrower because this is, of course, it's always smaller, right? Because n2 more than 1. So I should be a little bit more precise, okay? This is always narrower, okay? Because this n1 is at least 1, right? So this must be narrower than original, okay? So now the question we care is this guy, okay? A new random variable, this minus this. This we care. We care about difference of sample mean, right? Because x1 bar is a random variable, x2 bar is a random variable, bell, right? So turn out our formula we said this is also a bell. Okay, maybe I should be a little bit more careful. It's a little bit more fatter. Okay. And this is just mu1 minus mu2. Okay. This is due to the structure, right? And the variance has add up. Okay. That is the formula we have here. Okay. So this is the, once you understand this, things become very easy because we just rely on this thing. Okay. And why we care about this? Because we want to answer the question like the following. We want to see, let's go back to the question, and then we will see why we go back to this graph again. We want to care about this question, okay? Remember the question about the man and woman in China, how much do we need to pay for the product? If you are the sales manager, you want to know, do you want to have different marketing or sales campaign for men and women? Do you want to design different product for men and women? If they want to pay is different, right? Suppose man is more willing to pay than woman for car, right? Then probably you want to design a different type of car, right? Which might be more faster, more cooler, more different type. If woman want to pay more, then you want to make it more lovely, make it more kawaii, make it more fun to drive, right? So that is a different thing, right? So you want to take a difference, whether the difference between the two samples in terms of mean, right? Or as a sales manager, you want to see whether store A doing better than store B, right? If A is better, maybe you want to spend more money on A, right? Or is it justifiable to pay more rent for store A than the B, right? And similarly, right? The marketing manager, is it A better than B, right? If you want to spend your marketing effort, where to go? Or more recently, as a scientist, right? Or government, is vaccine A better than vaccine B, right? And you want to promote which vaccine, right? Or wearing mask is better than manual mask. You want to understand that, right? So that is a thing we always want to compare in the many business or real day scenario, right? So that go back to the question. We want to test the hypothesis whether the mu1 or mu2 are different, right? And exactly whether this is 0 or not, okay? And this is exactly what we have done, right? Even though you start with 2 samples, at the end, we end up with 1 sample, okay? It's 1 bell, there's no difference, right? As long as we make assumption, the 2 populations are independent, the bell, then everything goes to the bell again, right? 2 bell become 1 bell. 1 bell we can know how to do, right? So let's go to the question again, okay? So I mean I should have a break, but before break, I have to mention what is the difficulties here. Okay, the difficulty here is how do you get this two, right? If we know this two, this shape is done, then everything is easy. Just use the Z test, very standard. We have talked about that. Okay. The problem is we don't know this guy in general, right? We have to use S1 and S2, right? So with replaced by later you will set the break, right? These two, how do you measure it, right? Come from S1 square and S2 square, right? And use a T, right? And there is some complication whether originally they're the same or not, okay? If you make the assumption, which we do first round, then we can do better than this. Okay, there's a formula to combine that to estimate sigma square. Okay, if you cannot make that assumption, then you have a other formula, okay, to do it. Okay, so the complication only lies on whether you can make the assumption they're equal. If they're equal, okay, that's the same shape originally, you can make a better estimate. It's a different method. Okay, if they're different, you cannot make the assumption, and there's another formula. So there's a different formula depending whether you know this. Okay, but again, it's just applying formula. So all the procedure you know, there's some complication about the formula there. So it's rather tedious. Okay, but just look at the formula to apply. Okay, so let's a break of 15 minutes, and then we come back. Okay, I open the U reply. You can answer. Feel free to walk around. I guess it's a little bit cold, so walk around can keep you warm. You need to. I walk around to see if there's a question. We will resume at 10:35. So let's see. Can I provide set table? We can. Okay, I'll try to do that. But any set table, there is no different because I just compile from Excel. So you can create your own. You should be able to create your own. But in the case you really want, well, you can just download anything. But if you really want, I would just try to do that. Remind me if I didn't do it because I negative can be normal, but I haven't checked the assignment yet. But if that's the case, I'm not sure. For assignment question, ask the TA. Okay, please. I really don't know the assignment question. Okay, because the TA helped me to modify the question every year, so you have to ask him because I didn't actually check carefully. So I mean, please ask the TA. How to determine x0? So very simple. Our class x0 is always equal to something. It's a simple hypothesis, right? It's sample mean equal to some number. That's it. That's what we do. Nothing special. Okay. And the alternative is more than or less than or not equal to. So that is the way we do. I hope that become clear. Deadline of project. So I'm sorry I didn't ask, but I would say I have 99% confidence, or at least 95, that we can at least extend 7 days. Okay. Whether I extend more, then I have to ask the other class whether it's okay to say 10 days at least. Okay, maybe 10 days, or I don't know whether we can do 2 weeks, but let's see. But at least will be 7 days, at least 1 more week. A project, yeah, extend. But do remind you that the page limit is upper limit. Okay, 2 pages at most. Of course, you can put something more. It's okay, but I recommend you just keep the page limit. Because I will only read the page limit. Unless I have doubt, I will read the appendix. But just pick everything in page limit. Okay, it's not more the better. Okay, you're doing a business report, so actually less is better. Okay, I mean it's the ratio, right? So that means that if you have more people in the group, you don't have to use up the page limit. Rather, you should make your report more concise, right? Imagine as I said, right, at the beginning. Imagine I'm the boss or the CEO, right? Or your client. I'm not going to read that many, right? Because I'm reading so many reports, right? I have to be something capture your attention, right? So make sure that your report is well written, rather than extend as long as you can. Okay, make it as precise and concise. Exam, I really can't extend the deadline exam, right? It's in 1 hour, so I cannot extend like 2 hours or 3 hours. I really can't do it. I want to make it 1 hour. Is also very simple, not so stressful. So I just to reiterate, the final exam will be not very difficult. The problem is like you have to do it faster, because you do the revision, then you should know how to operate. Okay, it's not something that very tricky question, but just like a standard question, you should know how to do it, but you would just say you do it faster. That's the thing. Okay, and if you know, then I think you have enough time. And I'm asking our TA to go over my exam again to make sure that things would be enough time if you know well. Okay, but don't worry about that. It's all relative, right? So if you find a short time, other people find it very short as well. All right. So I just try to see how well you're doing. So is there any formula compare? Yeah, we'll do that now. Okay, compare mean with the formula. Good morning. Yes, good morning. It's exam. Yeah, it's open book, open notes, open everything. But the unfortunate fact is you have to print out. We do not allow electronic device. You bring your calculator. Okay. Detail of syllabus or final be released. What does that mean? I mean, basically is we cover everything covered in the class and the slides. Those things we don't cover, even if slide, you don't have to worry. So the syllabus is what we said, okay? And some of you may worry that we only have 4 class left, actually 3 or 4 more class left. So are we going to finish everything? The answer is we may not, but don't worry. If we don't cover, it will not be there, okay? And I cannot conjecture how fast we cover stuff, but we try to cover things. And if I think it's not enough, I will cut out some of the parts, okay? And only the thing we taught, it will be there. So, but at least I think that we, the regression and the ANOVA, supposed to have assignment for that, but we don't have time. Probably that assignment, I would just give it for free. You just do it. I give the answer and the solution and the question at the same time. So you can check it out, okay? So that would not, so this assignment supposed to submit on the 30th of November with the last assignment. Okay? Suppose an assignment, but that one I will just give it for free, okay? So everyone got full credit for that, okay? So although, because of the, so good, everyone know it's Friday. Yeah, it's typically sunny and windy. Yeah, that's good. So most of you think the speed is appropriate. It's okay. Of course, some of you still think a little bit. Overall, it's fine. So do you know in Africa, every 60 minutes, then it's 1 minute. The second is 1 minute. Okay, that's good. Yeah, I think here in Hong Kong is a little different, right? Every 60 seconds means we have 2 minutes past. Oh, so cold. Yeah, it's pretty cold now. I mean, stay safe, stay warm. If you need to walk, you can just simply walk. It's okay. I mean, make sure that you don't feel cold. What's ASM? Assignment. Okay. Yeah, so as I said, I queue 1 assignment for you. So I queue 1 assignment. So you said no, that we only have last assignment. The assignment 6 will be queued by me. So I will release the assignment with the answer. So last assignment on regression ANOVA, you will get it for free. Everyone got full credit for that one. So I queue 1 assignment for you, right? And the deadline for the project also extend, right? At least for a week, but I don't know how long we extend. I'll ask other section. I'm sorry that I forget to ask. Hopefully I remember that. So does anyone have power bank? I mean, please lend to your friend if there is. I don't have a power bank, sorry. If you have anything. So if you have anything, please, maybe a charger can also charge here. I don't mind it. I'm sorry, I don't have power bank with me at the moment. Yeah, that's okay. Any question? So now we just go back to this one, okay? There's a bell here, right? We have man and woman, right? They follow the bell curve. I want to ask whether actually the mean of men and women are different, right? Why we care about that? Because we want to know, we want to actually have different marketing campaign or separate the market differently, right? And of course, some of you asked in the break, why I just care about the number I found. If they're different, they're different. Again, because of randomness. We want to make sure that the difference not coming from the sampling mistake, right? When we draw conclusion, it's based on statistics. So that means that anything is possible. So we have to be very careful when we draw conclusion, okay? So let's go to this directly. So just remember, what we do is no different from doing 1 sample. The only complication comes from how to estimate this and what t-table look at. So we have to be careful on that part. Otherwise, everything is very simple. Okay, nothing new here. So the formula is here. So slightly a little bit more complicated, but So the first thing we do when you compare two samples is we make things as simple as possible, right? That's how we start, right? Make a simple case. The simple case is sigma the same. Okay, let's go back to the picture. It actually means what? We assume the boys and girls are the same shape, right? So this same shape, but this can be different still, right? Because depending on the N1 and N2, right? Depending how many boys and girls I have. If the same, then same, but can be different. Still, right? Still this different. But originally the boy and girl are the same shape. Okay. And in that case, okay, if you recall, they're the same. So you have the boys sample SD, girl sample variance. They are both good estimate, right? They have no problem. So the question is which to pick, right? They are both unbiased estimate, right? Using the boy, look at the boy sample variance, the girl sample variance, can actually measure the shape. Okay, which one is better? Okay, both are unbiased. Okay, and we learn efficient, right? This turned out to be the efficient one. It's some average. The formula look crazy, but if you forget n-1 first, so forget n-1 in your mind, just temporarily forget n-1. So -1, forget about that. Well, okay. What do you see here? What do you see? Okay, you see here is a weighted mean, right? The weighting is proportional to the sample size, right? N1 and N2, right? N2 is a fraction, right? Suppose this is 0.4 and this is 0.6, right? If this is 0.3, this is 0.7, right? So add up to 1. It's a weighted average, a weighted mean, okay? And you ask what is doing here? Here is very simple. Suppose N1 is very big, a lot of boys, very few girls, right? That means that your variance come from boy will be better estimate, right? So that's why you put a lot of weight on the boy, right? If a lot of girls, they do the same, right? If N1 equals N2, right? Means same number boy and girl, you will use half of the variation in boy and half variation in girl as a good estimate, right? So that is why this SP square, right, is the best estimate for sigma, right? So once we have that, everything becomes very simple because now we can do the T, right? We know this guy, and put the formula, that's it, right? So let's go to the formula. Forget this is the proof, but I don't want to go ahead, right? So what we do is, right, you take a difference over the square root of what you did, okay? The only troublesome part is which T table look at, okay? Is M is the sample size -2, okay? And that's it, okay? So they can see it's not complicated, but just different formula there. So let's go to the example, then you will see how it do in practice. But do remember that there's nothing new there, okay? Only different formula because of the way we estimate sigma, okay? And because the way I estimate sigma, this becomes this, okay? So only this slightly new thing there, right? Because this is just the square root, right? Replaced by the sample. So you did the same all the time, right? So let's go to the example because example actually tell us how we operationalize that, okay? So again, we have the same idea with the normal distribution, right? Variance, and we have one sample is like this, and the other sample is like that, okay? Let me do it here, okay? So let me write down what we have in the sample, okay? What we have is the following: we're boys. How many boys we get? We have 50 boys, okay? And among 50 boys, how much they want to spend on the product is 40. The sample variance, sample SD is 4, okay? And now with girl, how many girl we got? We have 40 girls. How much want to pay? 42, okay? S2 is 3, okay? Okay, this is the question. Okay, we have here. Now, what is the hypothesis here? We want to see if boys and girls are the same, and the alternative is boys and girls are not the same. Right? Just to recall that the graph we have drawn just in the previous slide, this one. Okay, I just draw it here. Okay, what we have is, maybe I use the other color to make green, right? X1 bar minus X2 bar, right, will be mu1 minus mu2, right? And this is sigma. Remember, we don't have 1 here because they're same, right? Right, so this is the shape, okay? And note that under this is 0, okay? So the question would be, now the data tell us is 40, that's 42, okay? So which means that we're here, right? It's 40 minus 42. So the question again is it small enough? Use alpha, right? But of course, you remember it's two-sided. You compare to alpha over 2, right? Is this less than alpha over 2, right? If that's the case, then we reject. If not, then we don't. So you can see they're very similar, right? If I know the sigma, then we're done, right? That's very simple. The only troublesome part is we don't know sigma, right? But luckily, remember what we do is we have t, right? Right? And this is 0. The only complication is what is this guy, right? And how to do it is you have to convert, you have to take a difference, right, over the square of this guy, right? How to convert this is -2 minus the mean, which is 0, right, over the square root of this guy, right, and replaced by the sample version. Right? This is how we do, right? This is how we convert to this guy, right? But what is the S? What's S here, right? And of course, you may attempt to use 4 or 3. That's fine, okay? Either of them would work, right? But the thing is, we have a better estimate. Not use 4 and 3, somewhere between 4 and 3. Okay? How do you do that? Remember the formula. The formula will be, you use SP. How to use the SP here? SP square will be somewhere between 3 and 4, right? 4 square and 3 square, right? And we do it is based on the sample size minus 1, the weighting, right? Sample boy has 50, right? Get the weight 49. N2 is 40, get the weight 39. So it's 49 plus 39 and 39 over 49 plus 39. Okay? It just, the weighting it got, it's just the sample size minus 1, right? The denominator is the same. It's a weighted average, right? This got the weighting of 49, this got weighting of 39. So that's a weighted average, right? It's a weighted average, right? And then you're done, right? Then you can figure out this number and we can calculate that. Okay, so let's go back to the slide. The slide already calculate for us. So this one is 12.8, right? And then that turn out this guy, just plug it in, is -2. Okay, let's go back to here. So this guy is called -2.6. Okay, and the question is this area multiplied by 2 more than or less than alpha, right? That is the easiest way to do, right? But the question is, what is this T what, right? Which T table looking at? T table looking at is N1 plus N2 minus 2. So it's 50 plus 49. minus 2 is 88. So this is the part that is tricky, and this is part is tricky. Only these two parts tricky, but other thing is follow the same, right? There's nothing new, but only these two. Okay. You will ask, okay, why so complicated? Okay. If you do Excel, everything directly gives you answer. Okay. But I need to explain why we have this answer, right? If you do Excel, it's already there. Okay. Everything calculated directly for you if you try to check it out. But we'll do it anyway to understand what we are doing. So how to get this area? Very simple. Just T this, right? Negative 2.6, 88, true. Okay. Just don't forget to multiply by 2 because it's a two-sided one. Okay, because what we have two sides, right? If it's the left side, then it's fine. Right? If you hypothesize that man is less than woman, then this is you compare alpha directly, right? But if you both sides, then that's what you do. Is that clear? Oh, be careful. Is there any question? So let me go back to here, right? So this is the p-value, right? Turn out to be less than 5%, then you reject, right? So you say man and woman are different, right? This value, okay? Or you can do critical value. I'm not going to do that, but I think you are okay with that already. We do so many times, okay? But what I want to point out a little bit is the critical value is this guy, okay? Probably you may have noticed, okay? When you do two-sided tests, the critical value gives you confidence interval, okay? As you can see here, the confidence estimate is here. The denominator is here, right? The numerator is here, okay? Just to remind yourself what is confidence interval, right? If you want to ask what is the difference between man and woman in terms of the spending, right? Your point estimate is -2, right? Man is less willing to spend compared to woman by $2, right? Or maybe 2,000, depend on the unit, but that's what we have, right? But if you want a interval estimate, right? You go left and right by 2SD usually, right? That's what we have. It's SDC. This is this. Okay. So when you do two-sided tests, okay, immediately actually you can do two. It's a confidence interval, the same thing. Okay, the same thing. I think if you check it, so that's why the form is like here. So that's why I kind of have the slide in this one, right? Although I don't put it, but I think it's very clear that it's the same thing, right? Because remember what's confidence interval estimate, right? Is we get this number, right? We construct this interval, and this interval has high probability included. The same thing, right? Because the data here, whenever your data you got, right? Data here, you construct the interval, right? The same thing, right? We will include that, right? So that's the same thing. Is that okay? If there's no problem, then we go to another one, other formula. Okay. This formula indeed is actually it's more easier to understand. The reason is now they're not the same, right? Then you just use whatever we have, right? Just go back to the question here. So slightly actually even easier. The reason is they're not the same. So you just don't need to combine, right? So let me draw. Then you just keep whatever you have, right? Instead of SP, use S1 and S2. That's it. So let me go to the question again. and convince you this is the case. I think the example the same. Yes. So that is become easy. Okay. Now in this one, right? There's no duplicate. So maybe I have to draw this again. Okay. So let me do it again about the question. Okay. Again, I have boys. Okay. The data I have is 50 boys. Okay. I have sample, the mean is 40. Okay. This sample SD is 4. And I have I draw again here. And I have 40 women. Okay. And they're going to pay $42. And the sample variance is 3. Okay. This is common data. Okay. And now we no longer say they have same variance. Okay. So the graph will look like that, right? Just following from the graph we have is x1 bar and x2 bar. Okay. And they're the same, mu1 minus mu2. And this is sigma 1 square for n1 and sigma 2 square over n2. So we don't have the sigma same. Okay. And do remind you we have the same here. Mu1 equal to mu2 and mu1 not equal to mu2, right? Under this is 0. Okay. So that's a question. And again, what we have is -2, right? We want to know this area multiplied by 2 is less than or smaller than alpha. That's our goal, right? Same thing. So that is very simple, right? We know that there's some way to convert to t. This is 0. And we draw the thing and how to convert that guy here, right? Same thing, right? It's -2 minus 0, this time from the mean, right? And you take a square root of this guy, right? This guy is S1 square over N1 and S2 square over N2. Because you don't need to do further, because there's no way you can combine the two. They are different, right? Because S1 is good estimate of sigma 1 square, right? S2 square is the best estimate of sigma 2 square. That's what we can do. Okay. And then we calculate this number. Okay. And this number is what? Let's go back to the question. The question tells us this is 2.7. Okay. So it's -2.7. Okay. This number is here, right? Sorry. This number is here. This number is here, right? Everything is there. Okay. You can do this number, 2.7. So the only complication is which one to look at, which table look at. And this is where this most complicated thing goes in. Okay. And in undergraduate textbook, they don't tell you how to do it. Okay. And they don't explain. Okay. There are many formula. You can pick up this V. And the one we use is the formula that you can try to read it if you don't have enough sleep. Okay. The formula is tables like this. Okay. Which table look at come from this crazy formula. Okay. And what it is, I don't know. Okay. I don't know what it is, but someone, they prove it, very complicated formula. Okay. This is very complicated formula. Actually, this complicated formula is younger than me, only invented 30 years ago. Okay. Relatively new. So not something very old. So very recent advance. So we know how to do it precisely. Okay. So if you ask me why, I don't know. Just a formula. Okay. We know N1, S1, S1, whatever. Okay. And in this particular example, turn out this guy, you plug in the number, right? Just to explain a little bit. The number, this is S1, right? And, oh, sorry, I should use other color, right? Because this is S1, right? And these are N1, okay, and this is S2, and these are N2. Okay, I hope this will be better, and you can see this is smaller, okay, and it's always smaller, okay, and in this case it's just one less than the previous case, but in general this one can be very small, okay, much smaller than N1 minus N1 plus N2 minus 2. Okay, this is usually tend to be smaller and way smaller, but in this example is not much different. Okay, okay, and you do the same procedure, right? Basically, just know which table to look at. It's 67. You compare the alpha, and you're done. Okay, so that's why it's nothing new here. Just another formula to check, right? Another way to estimate the sigma. Another table to check. Okay, so there's nothing very new here. So that's why I spent a lot of time to review this earlier this class, because you have to know the procedure, right? Because the procedure is always the same. Is that clear? So I still have 10, less than 10 minutes, but I think we can finish the next one, because the next one is very simple. Just conceptually more complicated. But before we go there, but let's wait. Is that okay? Now we are done with this. So let me go to the other one. Okay, another type of thing. Okay, now for this one, I would like to draw a picture to tell you the idea. I think it's very simple. The idea is following. Okay, the question would be, usually the question is, what we often care is the following. Okay, one question would be, there are a bunch of boys. Okay, some boy, they go to CHK. Okay, and I look at their GPA. Okay, how they're working. Okay, how happy they are. Okay, how happy they are, so on and so forth, right? Whatever you're looking at. Now, I have the same group of boys, okay? But after 1 year in CHK, right? They got a girlfriend. Okay? The question is, I want to look at, after they get a girlfriend, are they more happier or less happy? Or they have higher GPA or lower GPA, right? Is in a relationship help you study better or worse, right? They may go to library together, or they maybe go to KTV together, right? We don't know, right? So the question, right? Or other question is, they are guys, they are good friends in high school, right? They spend each other playing basketball. Okay, now they have girlfriend. Do they still spend the time together, right? Or they have girlfriend and no more friends, right? Right. Now the question is, how do we measure that? We care is the boy number 1 here is same as the boy number 1 there, right? Boy number 1 here, boy number 1 here. Boy number 2, number 2, number 3, number 3, right? So we directly compare how happy they are before and after, right? The same guy, right? The same guy before and after. So we call this D1, this is D2, right? Because this is X11, first guy before, this is X21, okay? So D1 is X21 minus X11, right? So it's how happy they are after with girlfriend and before have girlfriend, right? So D2 the same. X21, X22 minus X12, okay? So and so forth, okay? And it's very simple. As long as we assume this follow a bell, then we are done, right? Because sample average, okay? if we are trying to say D, or called mu of D, right? Mu of D, the sample, right, is 0, is here, right? We are trying to look at the data, use the standard t-test we have done, right? We are done. Nothing new here, right? Although we have data of 2 different sets, right? Different time, we can match them, right? And with a difference between them, right? It's still one sample, right? Although we have the GPA before they have girlfriend and after girlfriend, we know the student ID we can match them. Take a difference, even though we have 2 sample data, actually it's 1 sample. As long as we are assuming that the difference follow a bell, done, just 1 sample. See, right? There's nothing new there, nothing new. Just conceptually, we have 2 sets of data, but we match them, then we're done. Okay. Do note that this is because we can match them, right? Actually, this is what happened in science, right? We have, we do a biology experiment, right? We have 2 plants, right? They're very similar, almost identical. That's why you can Mr. 1 and Mr. 2, right? The same. Then one experiment receives some treatment, right? More water or more sunlight or low sunlight, right? You compare the 2, right? Take a difference. And you see if it's different from 0, then you can draw a conclusion. Okay? And you can see the example is very straightforward, right? I have a medical test, treatment group and control group, right? And you want to see that there's actually the treatment has meaningful, right? Look at the mean, look at the SD, right? And sample size, do the same technique we have done. It's done, right? So they're exactly the same thing here. There's nothing new from that one, okay? So I see you next week, okay? No more to say anything. So I will go again this example a little bit more further, but you get the idea. There's nothing new there. But I will repeat this again, okay? So I see you next week.